Good morning, future presidents. Today we are talking all about sound and sound waves. So let's do a couple definitions and then we'll get to some cool demos. Sound. So sound is what we call a longitudinal or compression wave. Okay, and sound can be transmitted through any medium that has molecules. Okay. Okay, so sound is transmitted by the vibration of molecules. So that means it can be transmitted through gas, liquid, or solids. Okay. Which fits our everyday experience. We know that sound travels through us through air, but we can also hear sound through walls, and you can hear sound if you're underwater in a pool. So sound can travel through any medium with vacuum. With molecules, but not a vacuum. So sound cannot travel through space. Okay? It needs a physical medium with molecules to travel through. Okay? So what do we mean by a longitudinal wave or a compression wave? Well, so in many ways, sound can be thought of identically like the waves we were studying last time, the waves on a rope, or the waves in water. Okay? But the molecules wiggle in a different direction when the wave passes. So a longitudinal wave or a compression wave is formed when the wave, the elastic deformations, instead of being side to side, are along the direction of motion. So I'm going to create a compression wave here, okay, and send it traveling back and forth down the slinky. Okay, let me stop it and start it again. Okay, so if I form a compression in this, so I'm increasing the density of this medium, in this case a slinky. The same thing happens to air when we're speaking. Okay, we're compressing the air. Okay. We form a density wave or a pressure wave. A compression wave is traveling along that medium. Okay. Other than the direction in which the medium is moving, in this case, each individual point is oscillating back and forth this direction. Instead of last time, it was oscillating back and forth in this direction. Okay. Other than that fact that it's oscillating in a different direction, these waves act exactly like the other waves that we were studying last time. Okay. Which means we can have traveling waves, periodic waves, wave pulses, or standing waves, just like we can have with the transverse waves we were studying last time. Okay. So, sound. Okay, sound can be thought of as a pressure wave. Okay, so it's got alternating regions of high and low pressure. Okay, so when we think about this model again of the compression wave, right? So when we have a compressed region that is traveling down the slinky, okay, followed up behind it is a region where the slinky has been stretched, so it's got a lower density. So we've got a compressed region and a lower density region. So in air, when we compress air, we increase its pressure. Okay, when it expands out, we decrease the pressure. So we can think of the wave traveling through air as regions of high pressure and low pressure. Okay. So if we draw a picture of that, okay, we can picture the wave traveling just like we did last time. Okay. But instead of these peaks being, the air moving side to side, what this is representing is high pressure, where the air has been compressed. So each one of these peaks is a high pressure region where the sound has compressed the air as it's traveling. And each one of these valleys is a low pressure region. Okay. Where the air has been rarefied as that pulse passes through. Okay, high pressure and low pressure, but otherwise this picture looks exactly like last time, which means these waves act otherwise exactly like the waves we were studying last time. Okay, so interesting tidbit, speed of sound in air. It depends on temperature, but at typical room temperatures, sure, I ran out of room, that's temperature. Okay, room temperature is, the speed is about 343 meters per second. That's about 1/3 of a kilometer, okay? So you can think also of it as it travels 1 kilometer in about 3 seconds. And you probably did this, or you probably know this in terms of miles, but this is one way of determining how far away a lightning strike is, right? So if you see a lightning strike and then you start counting and you wait to hear the thunder, okay, the difference in the times comes from that light travels very quickly, it's almost instantaneous, whereas the thunder takes a finite amount of time because it's traveling at a much slower speed. Okay? So if you see a lightning strike, you count 1, 1,000, 2, 1,000, 3, 1,000. Okay, so if you count to 3, you know that the lightning was 1 kilometer away. Okay? Or a lot of people know this in terms of miles, so it's about 1 mile in 5 seconds. So same idea. So sound travels fast, but it's much, much slower than the speed of light. Okay, so it's about 343 meters per second. Okay, so it's a wave. It's transferring energy. That energy comes from the compression of the air, transmitted through the pressure. We can start creating wave pulses, just like we did for standing waves on a rope or traveling waves on a rope. Okay? So let's imagine air inside of a pipe. Okay, so here's our pipe. Let's say this end is a closed end. Okay, so there's a pipe and it's got a closed end on this side. It's open on the other end. Okay, we can put a little plunger in there, okay, that we can move back and forth. Okay. So when we're moving that plunger, we're creating a pressure wave in there. So let's imagine we take that plunger and we push on it real fast. Okay. We make a little wave pulse. Okay. We're going to get a wave pulse, which is a high pressure. Okay. And then that wave pulse is going to travel down that tube at 343 meters per second, the speed of sound in there. Okay. So just like the wave pulse on a string, here we've got a wave pulse traveling through the air. In this case, we confine the air to this tube in preparation to start talking about some musical instruments that use this model. Okay, so a couple things about this. We've got a wave traveling in a medium. Okay? So the wave is traveling through the air. There is a restoring force. Remember last time we said all waves travel due to 2 factors. One, there is a restoring force, and one, there is a mass density. So here the restoring force is the pressure of the air itself. Okay, if you create a region of higher pressure, it's going to try to expand and equalize out. That's a restoring force. The inertia term, or the density, is just the density of air in this case. Okay. So that wave is carrying energy. We've compressed the air, so we've done work on it. It's carrying energy that's coming down to the end of this tube. Okay, so when it gets to this end, something's got to happen because it's got energy, and that energy isn't going to just magically disappear. Okay, so this wave is going to reflect, just like it reflects off of a rope if it comes to a fixed end. Okay, so we're going to get a reflection there of that wave. Okay, which for sound we often call it echo, but it's just a reflected wave, just like the wave on the string. And we have that energy being transported back through the medium in the other direction once it's reflected. Okay, so remember last time when we had waves on a string and we had reflection, that allows us to change the energy, and then if we put two pulses on there, right, we could trade it back and forth and create standing waves. So just like on a rope, we can create standing waves in that pipe. Okay. We're going to get energy being transported back and forth, okay, reflected off the ends and interfering to create positive and negative regions of pressure. Okay, so there is one difference between the strings, though, which is that the standing waves we can get in a pipe like this are going to depend on whether we showed here a closed end, okay, but you actually get reflection off of an open end as well, okay, but the reflections are going to change, okay, depending on whether it's a closed end or an open end. So the standing waves we can produce will depend on what type of pipe that is. So let's just look at those two examples real fast. Here is a closed end. So that is just the picture we already drew over there. So here is our pipe, and we're not going to worry about the left-hand side right now. We're just going to ask what happens to a wave pulse when it hits that right side. So that's the closed end of that pipe or that tube. So we know that if we send in a wave pulse in here, that wave pulse is going to be a high pressure region, okay, and it's going to reflect off of this point here. Okay. So now when we talk about air being high pressure or low pressure, what we're talking about is physically the molecules are being compressed, right? So they're being compressed or they're being rarefied by being pulled apart. Okay. So let's imagine that this is the closed end of our tube right here. Okay. And we're going to send a wave pulse down, okay? And it's going to bounce back. Okay. Now there's one thing about this being a fixed end or a closed end, which is the molecules on this side, the molecules that are on the side of the closed end, don't have anywhere to move, right? If they have a pressure, increased pressure that's coming down, and that wave is traveling down to this point, okay, the molecules are getting compressed, but the ones at this point don't have anywhere to go. They can't move to that side because it's a closed end. Okay? So that means that the pressure will always be maximum at this point. Okay? There is, if the wave comes down, it's going to feel the full pressure at this point when it gets down there because the molecules can't move out of the way. So when we're creating a standing wave in this pipe, the closed end, I'm only going to draw part of the standing wave here. Okay, the closed end always is going to have the maximum pressure of those pulses, okay, because the molecules are maximally compressed. They don't have anywhere to go. So that means the closed end in a standing wave is always going to be a pressure antinode. Okay, it feels the maximum pressure oscillations. Okay, so remember with that can be so I talked about it as the maximum pressure, right? Because when it's getting compressed, these molecules on the closed-end side don't have anywhere to go, so they feel the maximum pressure. Likewise, when it's getting rarefied, right? So imagine the wave pulse is coming backwards. So there's a low density region here. There is no molecules on this side, okay, coming in from the closed end to fill in that little partial vacuum there, which means that it has the maximum low pressure, right? So that's why we have an antinode here. It goes between the maximum pressure and the minimum pressure. Right? So let's think about by contrast, what an open end looks like. So the open end of a tube or pipe. Okay, so here we've got a pipe similar to the one above, except for we're not going to close this end. This end is open up to the room. Okay? So that means it can feel the room's pressure at all times, okay? Which means if we send a wave down here in this open end, okay, its open end has molecules that are free to move. So they can adjust to the pressure changes. Pressure. Okay, so there are a lot of molecules on this side, right? To either fill in a vacuum or allow the compressed molecules to expand here, okay? Which means that at this end, the pressure never really changes. It always stays near the ambient pressure in the room. So in this case, the pressure stays near room pressure. It is absolutely free to change. There's nothing there that is forcing those molecules to compress or expand, okay? Which means that that is the pressure node. Okay? Remember, a node on a wave is a point that doesn't change, and a standing wave is a point that doesn't change. In this case, the pressure doesn't change because it's always open to the room pressure. Okay? There's no wall here that is allowing those molecules to compress or rarefy. Okay? So closed end is a pressure antinode. Open end is a pressure node for a standing wave. Okay? And this has a big effect on musical instruments, okay, which use the variation between the closed end and the open end to produce different types of sounds or harmonics in the instruments themselves. So let's look at that real fast, and then we'll do several demos of these. Okay, so let's see. Let me come over here. And let's do examples of an open-end pipe and a closed-end pipe. And see how the standing waves differ in those two. So first off, I should say that so wind instruments, also organ pipes. So wind instruments are just resonant pipes or resonant tubes. Okay, and they come in two flavors. There is the, I'm going to move this up in 1 second if you're having trouble seeing this. There's two types. There's the open tube. Okay, and the open tube looks like this, no closed ends. Okay, and it can take standing waves, but they require that there are pressure nodes at the ends, and closed tubes. Okay, which really are just closed at one end. We need some way of exciting those waves. Closed ends have closed at one end, open at the other, which means that we're going to have a pressure node at the open end and an antinode at the closed end. Okay, so let's look at the standing waves that can form in these two. Let's do the open tube first. And a common example of an open tube instrument is a flute. So a flute is effectively open at both ends. Okay. So I think one of those openings is the mouth, by the way, and the other one is the open end of the flute. So let's draw those pipes. Let's see. I wanted to fit these in here. Let's see if I can do this. So here's our flute. It has some length L. It is open at both ends, okay, which means that we have to, if we try to induce a standing wave inside that, we have to have a pressure node at both of the ends. Okay. So that will affect what type of wavelengths we can excite inside that instrument, or inside that tube. Okay. And the longest wavelength we can have is one where well, we are always going to have a pressure node at both ends, but the longest one is we can have a single antinode in the middle. So the longest wavelength, or the lowest frequency we can get, is a standing wave that looks like this. Okay, so it's got a pressure node at both ends and a single antinode in the middle. Okay. So that means the wavelength of this, let's call that lambda sum 1. This is going to be the fundamental frequency again, or the fundamental harmonic. The wavelength is just going to be equal to, so this is half a wavelength from node to node, so the total wavelength is going to be 2 times the length. Okay, and then remember the frequency, let's call that f sum 1. That's going to be the fundamental harmonic. Okay, remember that's the speed divided by the wavelength. Okay, the speed we know is 343 meters per second. So it's v over 2L. Okay, and this is the first harmonic for that flute. So that is the lowest tone we can get, okay, for that length of the flute. So let's look at the next one. Okay, once again, we have to have a node at both ends. Okay, this time we had one antinode in the middle. We can do the next one, which would have 2. Okay, so there is the next one we could fit in there with a node at both ends. It has 2 antinodes. It has 1 node in the middle. In this case, the wavelength is just equal to the length, so it's half as long as the wavelength of this one, which means the frequency is twice the frequency of the one up above. Okay. So we call that the second harmonic. It has twice the frequency of that lowest pitch, okay, that lowest note that we can produce. And then the next one so we had 1 antinode, 2 antinodes. So the next one we could produce would have 3 antinodes. If I can draw that right. Okay, so it looks like that, sort of. Okay, so in this case, the wavelength lambda sub 3 is equal to, it's basically equal to 1/3 the wavelength of the fundamental. Okay. So that means the frequency is 3 times that first one. Okay. So I think we got enough to see the pattern there. We can create harmonics in there. So the first harmonic has a frequency f1, which is equal to the speed of sound over twice the length of that tube. And then the higher harmonics, f sub n, is just equal to n times the fundamental frequency. Okay? So n is the harmonic. This is the nth harmonic. And for this open tube, n can be equal to any integer. So it can be 1, 2, 3, 4, 5, on and on. OK, so that is for an open tube. We have a fundamental frequency, fundamental harmonic, and we can also have harmonics that are multiples of those. Okay? So the harmonics that are accessible to an instrument defines how it sounds, because when somebody blows into a flute, the primary note they are creating, okay, is the fundamental, okay, but they also excite the harmonics. Okay, and what harmonics are available and how much they get excited, how big their amplitudes are, will depend on the sound or the timbre of the instrument. Okay. So let's compare that quickly with a closed tube and see how that differs. Okay, so closed tube is a very different configuration. And the primary example of that, or a primary example of that, is a clarinet, which is different from a flute in terms of its fundamentals. Okay, so let's look at this closed end tube. Once again, it has some length L. And the difference between the closed end and the open end is that, remember that an open end is a pressure node, but the closed end is always a pressure antinode. Okay? Which means that at this closed end over here, we always have to have the maximum oscillation, so the antinode, whereas this is still an open end, just like it was for the completely open tube, which means it's a pressure node. Okay? So when we're fitting waves in here, we have to have a node at this point and an antinode at this point. Okay? So the longest wavelength we can fit in there is a standing wave that looks like this, okay, which is a pressure node at the open end and an antinode at the closed end. Okay. And this is very different than the open tube, okay, because of the antinode at that closed end. The wavelength on this, well, you see we're only going from a node to an antinode, which is only 1/4 of a full wavelength. Okay, so this longest frequency on this one, the fundamental wavelength, is 4 times the length of that tube, instead of twice the length for an open end. Okay? So that means that the fundamental frequency, or the first harmonic, is the speed over lambda 1, that wavelength, which is the speed of sound divided by 4 times the length. Okay? So that is the first harmonic. For this closed-end tube. Okay. Now we can look what's the next longest wavelength we can fit in here, or the next longest standing wave we can fit in here. So there's our tube again. Okay. Once again, we have to have an antinode at this side and a node at that side. Okay. So the next one we can fit in, it starts off as an antinode at this end, okay, but it has to end as a node on the other side. So this is the next standing wave that we can fit in this tube. Okay. So this one has a wavelength. It is equal to It's a little bit of a different fraction than the other one. So this is only 3/4 of a wavelength here. So the total wavelength is 4 times the length over 3. Okay. Whereas this one is 4 times the length. So this wavelength is 1/3 of the wavelength of that fundamental frequency. Sorry, of that fundamental wavelength. So that means the frequency of this is actually the 3rd harmonic. Okay, the frequency of this is equal to 3 times the frequency of this one, which means that it's not the 2nd harmonic, you normally think. It's the 3rd harmonic. It's 3 times the frequency of the fundamental. So this is the 3rd harmonic. Okay. You might ask, what about the 2nd harmonic? It's not there. You can't create a 2nd harmonic in a closed tube. Okay? You can't create a wave that has, that would require us to have either an antinode at both ends or a node at both ends, and that's not the conditions for a standing wave in a closed tube. Okay? So there's a 1st harmonic, and then the next one is the 3rd harmonic. Okay? And then if we keep going, the next tube, the next harmonic we can create, once again has an antinode here and a node there. Okay? And it has to look like this. Okay. Antinode, node. The wavelength in this case is 1/5 of that fundamental harmonic up there. So that means the frequency of this is the 5th harmonic. Okay. Which means that we don't have a 4th harmonic for this closed tube. Okay? And so if you keep going on, fitting shorter and shorter wavelengths in there, you would see that we have no even harmonics for this closed tube. Okay? We have a fundamental frequency, the 1st harmonic. Okay, has a frequency which is the speed of sound divided by 4 times the length of that tube. And then the only harmonics that are available in that are the odd harmonics. Okay, where it's still a multiple of that fundamental harmonic, that 1st harmonic, but the multiple can only be an odd number. 1, 3, 5, 7, okay, on. Okay, so closed tube, closed end tube only has the odd harmonics available to it. Open end tube has all the harmonics. Okay? This is one reason that a flute and a clarinet sound so different from each other. Okay? Because, like I said, when you play an instrument, we don't just excite that fundamental harmonic. Okay? Depending on how the instrument responds, you will also get sound coming out at the higher harmonics. Okay? Depending on which harmonics are available and how strongly they are excited, how much sound is coming out of those different harmonics will change the sound of the instrument itself. Okay? And this is why we have so many different richly sounding instruments. If they all played a perfect note at the same frequency, they would all sound exactly the same, which would be very, very boring. So the reasons instruments sound different is because of the harmonic content. Which harmonics are actually available to excite, and how strongly they are excited. Okay, so let's do some sound demos. Okay, first, this is a example of a tube. Okay? And what I've got up there is a speaker. Let's see if you can actually turn it on. So, can you guys hear that? Okay, so that is coming out at 1,000 hertz, 1,000 cycles per second. I have no idea what note that is. Any brilliant music majors in here? A little bit lower than C? Okay. Nice. Okay, so that's, there you go, 1,000 hertz. This is you can think of the speaker up there at the top as being our little plunger, which is exciting sound waves in this tube. Okay. Now, there are waves in there, but they're not standing waves because we're not exciting it at the right frequency. Okay, so as I'm going to let water out of this tube, and I'm going to let the water drop. So when the water is dropping, we're effectively, let me turn this off for 1 second. As the water is dropping, we're effectively changing the length of that tube. Okay, so we're making it longer and longer and longer. So it's a closed end. We're changing the length of it, which means that we're going to go from hitting multiple standing wave patterns in that. So let me turn it back on. This is actually nicely marked at where these are. Okay, so, this is a very audio demo. So I'm going to let the water out, which is effectively making the tube longer. Okay. We're not getting much resonance now. Oh, I think I've got this on the wrong frequency. Let me do this again. What's 500 hertz? C flat. Is there a C flat? That's a that's a B. It's a flat C. Okay. We're going to get all the music people in here arguing. That's great. Okay, there. This is better. Now we're at the right frequency. Let me put this back up. Okay, now we're at 500 hertz. That's the right frequency for this demo. Oh. Okay, so once again, I'm going to let the water out of this. And right now, we're sending waves in that tube, but they're not the right wavelength to be standing waves. Or sorry, the tube is not the right length to allow standing waves produced. So let's change that length and see how much that we can, if we can detect the standing wave when it gets excited in there. So water's dropping. Oh, did you guys hear that? Much, much louder, right? So at this point, we're hitting this first resonance, okay, for the first standing wave pattern, okay, where the standing wave's actually excited in the tube. So we're getting a much stronger response from the air in that tube. If we keep letting water out, we're going to go past the resonance for this frequency. You can hear the sound is dropping, the amplitude's dropping. Okay, so let's let it fall. Okay. So we're still sending waves down that tube, but they're not standing waves. They're not the right frequency for the length. And so we're not getting that feedback in the resonant pattern that we get for standing waves. Okay. Until we get to the next harmonic. Okay, you guys could hear it got much louder there, right? So that means we're increasing the length to get to this pattern. So remember, in this case, we are keeping the wavelength fixed. We're just changing the length of the tube, trying to get to these resonant locations. So the next one. So let the water keep dropping. We're changing the length. It's the wrong length for the standing wave at this resonance. There we go. So that's the next one. Okay. We could actually also use this to measure the speed of sound, right? So we know that, let me take it off the resonance so you guys can hear me. these marks are separated by about 20 centimeters, so that means a node to node, in this case, is about 20 centimeters. Okay? We are sending in a frequency of 500 hertz, so 500 cycles per second. So if we know the node to node length, it's about 20 centimeters. The wavelength is about 40 centimeters. The frequency is about 500 hertz. So, but if we know the wavelength and the frequency, we can derive what the speed is from that. I hope it's actually close to what I said. So let me put water back in this. You can hear as we go very dramatically past these resonances. Okay, so I wanted to try something else here, which I haven't done before. Let's play with it. I've got another one over here going into a speaker. So you guys can hear that, right? I wanted to, let's just figure out what is the audible frequency range. So right now this is about 1,000 hertz. So I'm going to turn this down. Very Star Trek-y, isn't it? Ooh, very low. This is getting very low. So this is about 50 hertz. Okay. That's probably pushing about the limits of our hearing, right? You could probably actually feel that vibrating a little bit if it were louder, so. A very low frequency. So that's about 50 hertz, so that's the low end of our pitch range, I'm guessing. Can you guys still hear that? I'm not sure this will go all the way up. Is that hurting? Is anybody about to explode? So this is right now about 7,000 hertz. Eight thousand hertz. You can still hear that? Kids. That's almost unaudible. 9,000. Can you guys hear that? You guys and my dog. This is already past my age. You lose your range as you get older. This is 10,000. You guys can still hear that? Pretty high pitched, eh? Let's see, I don't think I can change the range going up from this. So last time we were hitting those bars at about 15,000 hertz, which was above most people's range, even though there was still a few people that could hear that. So we have quite a wide range of frequencies, right? So that was like 50 to 10,000. Okay, let me turn this back down to where I need it to be. Okay, so sound. Any questions on that so far? No. Yes. So the holes, when you're playing a flute or another instrument like that, you're effectively changing the length of the resonance tube. So you can do a couple of things. You can effectively change the length of the tube by basically making pressure antinodes there, pressure nodes. So you're basically opening it up to the atmosphere. And you're also controlling where other nodes can be. So you're hitting where harmonics are by, say, opening a, if we suddenly open a hole right there, right, where it would have been a maximum pressure, suddenly that's open to the atmosphere. So it no longer can have a maximum pressure there. It can only have a node there. So it's affecting, basically what sort of wavelength can fit in there for those boundary conditions for the different instruments. So yeah, so the variation of the holes along there are basically changing both the length and where you can have nodes and antinodes inside the tube. Does that make sense? Good. Okay, any other questions? Oh, there we go. Yeah. Ah, okay, that's a great question. So yeah, this is the sound does travel through the water in here, but it's a very stiff medium. So that's so there is some energy that gets transported in that tube, but most of it gets reflected. So and it's kind of the same thing as let's say you had a nice loose slinky like this, right? And we connected it to like a really heavy spring on this side, like a shock absorber spring on a car or something like that, right? And if we tried sending, a wave down there like this, suddenly we're going to go from, what is a very, sort of floppy loose medium into a very stiff medium. And what's going to happen is that most of that energy is going to get reflected off of that big massive spring on this end. It's going to look almost like a wall there, just because it's so heavy and so hard to move. But there is a little bit that will be transmitted through, and the same thing's happening here. So there's a little bit of energy that's going into that water, absolutely. So, but most of it's getting reflected back in the air, just because it's much easier for it to do that than to continue down. So, yeah, that's a great question. So, you guys know what I'm in the mood for? Always. Quiz time. Okay, so wait, can I have this projector down here? This one is VGA1. Okay, does anybody not have a quiz slip? Raise your hand. I see you. Remember, good, yay. Let's see, do you have it switched over on this one? So this is VGA1, stage left. Huh. I know you're trying. Let's see. Unfortunately, I don't think I have the adapter for the other one. Oh, there you go. Thank you. You guys would have been so disappointed if we couldn't do this, wouldn't you? Okay, question 1. The strings of a guitar vibrate. Guitar. Is that very southern? Guitar vibrate at different frequencies. They have different thicknesses because A, a thinner string has more tension than a thicker string and vibrates at a higher frequency. B, a thicker string has more tension than a thinner string and vibrates at a higher frequency. C, a thicker, more massive string vibrates at a lower frequency than a thinner string of the same length and tension. Or D, a thinner, less massive string vibrates less frequency than a thicker string of the same length and tension. I'll give you guys a minute to read those. Okay. Next question. Question 2. How are standing waves and traveling waves similar? A, both waves transport energy in one unique direction. B, both waves have nodes that move with time. C, neither wave can be transverse. Or D, both waves involve oscillation of some medium. Standing waves and traveling waves. Okay, let's hand those over towards the ends of the aisles. I think the GSIs are already up there, starting to collect. Okay, wait, while they're doing that, can you switch over to this laptop now? Ah, perfect, thank you. Okay, great. So let's pick back up. And we're going to start talking about beats and beat frequencies. So Standing waves. Standing waves, remember, we saw were the superposition or two waves traveling through the same medium, and they were adding and reinforcing each other, producing a standing wave pattern. Okay? And here on the graphic, you can see it there, we've got two waves. We've got the blue wave and the gray wave. These have the same frequency, and they are traveling together at the right. So I turn this down very slow so we can see what's going on. But these have the same frequency, so they are overlapping, and the way that they're overlapping never changes. So remember that the red is the overlap, the addition of the two frequencies. So you can see where they are adding constructively, producing higher peaks, where they're basically the valleys are producing the lower valleys in the red when they combine together. So these are two waves at the exact same frequencies. So waves also will superimpose or add together if they're at different frequencies, but they produce very different phenomena. And we're going to do this audibly as well, audibly, that's the verb, right? Okay, so I need to adjust these, so let me turn these on so I can adjust them, and you can also hear the sounds. So this is, once again, 1,000 hertz wave, and I need to adjust its amplitude here. So I think that's good. And here is another 1,000 hertz. Okay, I think that's going to be good. So let me go back to the demo here. So here we've got the two waves that have the same frequency as each other, so they are superimposing, but you see that pattern isn't changing. They're always producing that single superimposed wave traveling to the right, the red one. Okay? Let's change the frequency of one of these a little bit. So one of these frequencies was just a frequency of 1. Let's change the other one by 10%, so it's 1.1. So it has a slightly higher frequency, so that means a slightly shorter wavelength, okay? Which means that the pattern they produce when they superimpose is going to differ. Because the wavelengths are different between these two waves, okay? They're both traveling at the same speed, and for the sound, it's going to be the speed of sound, okay? You can see, for example, right in the middle now, those waves are almost aligned to each other, okay? So that means the peaks are aligned, the troughs are aligned, which means the peaks are doubling up. So the red is the superposition of the two, which is at its maximum. And now it's reaching its minimum as because the two peaks are lined up and the two valleys are lined up. But the fact that they have different wavelengths means that that pattern is not going to stay constant. It's going to vary. And here in a few seconds, we're going to get to the point where they are anti-aligned, where the peaks of one are lined up with the valleys of the other one, and they effectively cancel each other out. And you can see that's coming up on the left as this thing slowly moves. I want to give you guys a good view of that. So right coming on the left right now is an example where they're basically anti-aligned with each other. The nodes of one, the peaks of one are at the valleys of the other one, so they're canceling each other out. And that red curve gets very low value there. Let me speed this up a little bit so you can see what that will look like at a higher velocity. I might have to play with this a little bit. There you go. So you can see that the red curve is a superposition of those. Okay. It will go from being a maximum superposition where they are producing the highest amplitude to points where they're basically canceling each other out. Okay. So they're going from highs to lows. Okay. The whole time the waves themselves are still oscillating just as they normally do, but the superposition is changing quite dramatically between a very large amplitude pulse to a small amplitude pulse. And let me change this even a little bit more here so we can see the big picture of this. There you can see the, now you can see the superposition there, the red between those waves, and you can see there's very dramatic variation in the amplitude. One thing to realize, though, is that that amplitude is changing. So how frequently it goes from being a very large, the red wave goes from being very large to being very small. That's the superposition of them. That amplitude is changing at a much lower frequency than the individual waves are oscillating. Okay, so that is called the beat frequency between the two frequencies, and it happens when you get the superposition of two waves that are slightly different frequencies. Sometimes they are overlapping and producing a louder sound for the case of sound waves, and sometimes they are canceling each other out when the sound basically disappears. Okay, so let me switch to the oscilloscope now. I don't think you need to do anything up there, Wayne. Hopefully this will just work. Okay, so here's the oscilloscope. This is basically measuring sound. So if I come over the microphone, my American Idol moment, you guys can see me talking up there. You can see the wave frequencies. You can see the different frequencies of my voice. Okay. That's not the demo I wanted to do. I'm going to send in 2 waves here. Okay? So each one of these speakers has a different frequency that it's emitting. Okay? Let me start them off with the same frequency. So these are at 1,000 hertz. So if I shut up, you can see the wave itself. So there is the first one. Okay. Here's the second one. Same frequency, 1,000. Okay, I'm going to change that one just a little bit. Okay, now it's 1,001, so you're not going to be able to tell the big difference of that. Now, let's put them both together. Okay, they have a slightly different frequency, so sometimes they're going to be overlapping positively, and sometimes they're going to be canceling each other out. Okay. Let me change the scale on this. I'm going to change the amplitude of this a little bit. Let me turn them both down. Might be a little bit more obvious. There we go. Okay, I'm going to change the frequency just a little bit on this so it's a little bit more dramatic. I have to play with this a little bit to adjust it. Okay, so now one's at 1,000 hertz and one is at 1,010 hertz. And you can see the superposition of those happening very quickly. But you can also hear it, right? You can hear it going loud and soft, altering. Okay? But that alteration is a much lower frequency than the sound itself. And if I change the frequency so that they're closer together, then the times when they overlap and the times when they cancel each other out become much longer, which decreases the frequency of the beats between them. Okay. So, for those of you who've ever played in a band or an orchestra, you know when you're tuning an instrument, you're not listening for the notes itself, you're listening for the beat frequencies between your instrument and the tuning fork or whatever the instructor is using to set the frequency for the note. So you're not listening for the tones, you're listening for the beats between the tones where it oscillates down. And as you get closer and closer to the frequencies being the same, which I'm trying to do now, you'll hear that beat frequency get slower and slower, okay? And then eventually it will completely disappear. Okay, now they're the same frequency, so you don't hear the beats anymore. You just hear the pure tones. Right? Now, let's say we overtune it, right? So I'm going to start tuning that string too much on my violin. This is bringing back nightmares to me. Okay. Okay, so as they go out of sync again, the frequencies start varying. You can start hearing those beats again between them, right? And if you have a very sensitive ear, you can use that to very carefully tune the instrument to the right frequency. See if I can do this, justify my years of orchestra. That's close. Yes! It paid off. I'm still tone deaf, but I can tune a violin. Okay, so that is the beat frequency between those sounds, okay? And the larger the variation is, the faster it goes. Eventually to the point where you can't even hear a beat frequency. So if I turn it up really far, okay? So now there's almost 100 hertz difference between them. That's beating so fast that you can't really hear it. It just sounds like two different notes being played together. Okay, let's see. I think the only other thing I wanted to mention is the Doppler shift. Let's see. Where are my notes? Oh, there's my notes. Okay. Okay, so any questions on beat frequencies? You can play that with soda bottles. Okay? You and your friend have soda bottles. You can put a little water in the bottom to change the resonance notes, and you can blow over them and hear the beat frequencies between them. So fun dorm experiments. Okay, okay, so last thing I want to talk about very briefly is the Doppler effect. And we're not going to go into a lot of detail of this. I just want a very quick explanation of that. Okay, the Doppler effect occurs when the source of a sound is moving relative to the observer. And so the common example of this is a train. So when a train is moving towards you, okay, the frequency it emits is higher than when the train is moving away from you. So you'll hear that very characteristic sound of a train, so a very high-pitched frequency transmitting to a low frequency as it moves past. Okay? So let's imagine we got a source of sound and an observer. So here's our source that's producing some noise, and here's our observer over here. And very simple explanation. If the source and observer aren't moving, so let's draw that case first. Okay? So if they're not moving relative to each other, then the source is producing sound waves, so those waves are just traveling out. Okay? These circles are meant to represent peaks in the sound wave pattern, so they're just spreading out with the speed of sound, 343 meters per second. Okay? And when they reach that observer, right, the observer is just going to hear each one of these peaks as it passes his or her position. Okay? So the rate at which these peaks pass the observer's position is going to determine the frequency that observer is hearing. Okay? Uh-huh. Meters per second, yes. Not meter seconds, meters per second. So that is speed. Okay, so let's just draw the picture if that source is moving. So that source is coming towards the observer. Okay. So same picture. There is our observer. But now this source is moving. So there's our source, and it's going to be moving. Let's have it moving towards towards the person on the right. So these are 3 different steps in time. Okay, so now what we want to imagine is what's happening to the waves that that source is emitting. So that source is emitting the peaks in amplitude. Okay? Those are going to radiate out from the source. Okay? But the source moves between the peaks. It moves to the right. So that means that the later peaks moving out are going to be centered more and more to the right as the source moves to the right. Okay? So the original wave that moves out might be centered around the initial position there. See if I can draw that. Okay? So that's supposed to be centered around this initial position. But the next wave will radiate out not from this position, but from where the source has moved to. Okay, from this position. So that means the second wave that comes out is going to be radiating from around this point. The third one will be radiating from around that point. Okay? That's not a very good picture, but I think we get the idea. Okay. So effectively what that means is that the waves are going to be bunched up on this side. Okay? So the peak-to-peak distance is going to be smaller. So this means on this side we've got smaller wavelengths. Or higher frequencies. Okay? So the observer, when the source is moving towards that observer, the frequency is going to go up in pitch. Okay? Likewise, if we had another observer that was back here, listening to the sound, the wavelength is going to be longer, okay? Which means that the frequency is going to drop. Okay, so when that source of sound is moving towards you, if it's emitting just a single frequency, that frequency will sound shifted up to higher frequencies because it's got a relative motion towards you. And if it's moving away from you, it'll be shifted down to lower frequencies just because the waves are getting either bunched up or spread out from the motion of that source. So, very quick demo. Another painful sound. We don't like pure tones. Okay? It's just a single note. Okay, you're going to alternating hear it moving towards you and away from you. You can hear the pitch going up as it's moving towards you and dropping as it moves away from you. And if I do it faster, I hope this string actually feels kind of old. I can handle this. You can hear a very dramatic shift in the frequency just from the relative motion. Okay? The waves aren't changing. It's not emitting a different frequency. It's just you're hearing a different frequency because those peaks are reaching you faster or slower depending on whether it's moving towards you or away from you. Okay, that is it for sound. Next lecture, we're getting into electricity. Awesome.